Okay, everyone, we are going to start a lecture on chemistry, which includes organic and inorganic compounds. I'll have to admit it is not the most exciting lecture that we're going to come across. Um, there's a lot of nitty gritty to it, but I'm going to try and keep the chemistry portion very basic, very simple, and very direct. This is not a course that is designed to make you chemists or biochemists. It is an anatomy and physiology course. However, before we get into the cells, we have to talk about chemistry because remember, you have chemicals that come together to make cells, and then cells come together and make tissues, and then tissues make organs, they make systems, and then eventually the organism. So covering inorganic and organic compounds is important, especially when we discuss the organic compounds like proteins, carbs, and fats, because the big picture to all this is when you look at a cell membrane is made up of those chemicals, those organic compounds. We're going to be talking about carbohydrates, proteins, and fats, but the body is also made up of water, which is inorganic compounds. All right, so just kind of lay down some framework as to why do we have to learn this? Why is this so important? And then, of course, we consume foods that have protein, carbs, and fats, and our bodies break those down through catabolic pathways. It breaks them down, and then we build them up anabolically to build up our tissues. So that's what metabolism is, right? Metabolism is composed of catabolism, breaking down, and anabolism, the building up. All right? So we're going to be talking about some fundamental concepts to chemistry, a little bit about matter and how it's organized, chemical bonds, how they're made and how they're broken, and then, of course, organic and inorganic compounds. So let's look at how matter is made up. So chemistry is the science of structure and the interactions of matter. And matter is anything that has mass and it's going to take up space. Mass is the amount of matter that a substance contains. Now, that's not the same thing as weight, right? Weight is the force of gravity that's acting on that mass. Matter is going to exist in a few different forms, and you kind of remember this back. This is some elementary information. So the three different forms are going to be solids, liquid, and gas. Okay, all forms of matter are composed of chemical elements. So we'll talk about elements as well. The elements are the substances that can't be split into simpler substances by ordinary means. There are 92 elements in nature, and 26 of the naturally occurring elements are within the human body. These are represented by chemical symbols. And some of you are familiar with these. So if we talk about sodium, right, which is Na, the Na from the word natrium, right? So if we were talking about sodium chloride, it would be NaCl, sodium chloride, which is salt. Now, four elements form 96% of the body's mass. So what are those four main elements? CON, C-O-H-N. The C is for carbon. The O is for oxygen, H is for hydrogen, and N is for nitrogen. So CON, C-O-H-N. There are trace elements as well, and these are present in very, very small amounts, such as copper, selenium, and zinc. Now, although these things are in very small amounts, they are extremely important. Very, very important. So copper Usually we abbreviate that as Cu, and then selenium is Se, and then zinc is Zn. Okay, and you're going to hear of these minerals, these trace elements, throughout the course with me. When we get into the cell, we will talk about, well, there's the cell membrane and there's a nucleus, and let's say this is a mitochondria. We'll just kind of make it like this, mitochondria. All of this stuff here, all of this fluid in the cell is cytoplasm, or intracellular fluid, and then there's fluid between the two cells. There's fluid between them, and this fluid between them is extracellular fluid or interstitial fluid. Okay, so this is a cell and this is a cell. And there is this antioxidant system that we all have to protect ourselves. Antioxidants. So what does damage to the body are oxidants, and to protect us, we have antioxidants. Foods very rich in color, like Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, all the foods of the rainbow, happen to be very rich in antioxidants. And within the cytoplasm, we have an important antioxidant system that's called superoxide dismutase. Superoxide dismutase. When it's in the cytoplasm, we have something called copper zinc superoxide dismutase, and it protects the cell membrane against oxidation. It's like bullets hitting the cell membrane. It'll make holes through it and it becomes very permeable, and it's very unhealthy for it. The mitochondria itself here, the mitochondria has an antioxidant system that protects it, and that's called manganese, not magnesium, but manganese, SOD, superoxide dismutase. So the mitochondria is giving off a lot of oxidation. It's giving off a lot of free radicals, because as it produces energy, there's an oxidative process. It's very natural and very normal. So the mitochondria, as it makes energy and it's producing oxidants, the mitochondria is protected against the oxidants because of this manganese superoxide dismutase. And if there's any damage that happens to get out of the mitochondria, or radicals or free radicals that make it out of the mitochondria, the cell membrane of the cell becomes protected by the copper zinc SOD. So you can see that even though these trace elements are in very, very small amounts, copper, zinc, and selenium, it's super, super important to protect us. You've heard of vitamin C as an antioxidant. It's super important because it helps to protect the most powerful antioxidant to humans that's called glutathione. And glutathione is extremely important. We can manufacture that as long as we have good protein in our system. And you've heard the saying, you are what you eat. It's not true. It's you are what you can assimilate, what you can digest and break down, and then the body can actually utilize those things. We know that if you swallow a quarter, you eat a quarter, you don't become the quarter. You're going to poop it out, right? It comes out the other end within a day or two. So it's not you are what you eat, it's what you can absorb and digest and assimilate and bring that into your tissues. So if you eat protein, you have to have good digestive enzymes in the stomach to break them down, and then those proteins are broken down into amino acids. So the amino acids called glutamine, glycine, and cysteine are needed to make glutathione, this powerful, powerful antioxidant. And then vitamin C is needed to help recycle glutathione. Glutathione is like a bulletproof vest, and it's getting hit by these bullets all day long. Vitamin C's claim to fame is in its antioxidant property because it helps to recycle glutathione to throw it back into war to take more bullets, more oxidation, more free radicals, if you would. Okay? So the elements are given these chemical symbols. If you look at oxygen, it's O, carbon C, hydrogen H, and nitrogen N. These elements make up the majority of our human body. If we look at oxygen, we look at the percentage of body mass. Wow, 65%. Carbon, 18.5%. Hydrogen, 9.5%. And nitrogen, 3.2%. And if you look at the significance of oxygen, part of water and many organic molecules, it's used to generate energy, which is ATP, adenosine triphosphate, a molecule used by cells to temporarily store chemical energy. Carbon forms the backbone chain and rings of all organic molecules. So carbons, lipids, which are fats, proteins, and nucleic acids, are all made up of a long carbon chain. So let's make this blue here. So we can have a carbon, another carbon, another carbon, another carbon, right? So as long as you have these carbons bonded together, that's a long carbon chain. We're always going to see that in organic molecules. Carbs, fats, and proteins, and nucleic acids, if you look at the Na in DNA and the Na in RNA, it's the nucleic acid is the Na. It's just ribose nucleic acid or deoxyribose nucleic acid. If we look at hydrogen, it's a constituent of water. Obviously, it's H2O, so it's a constituent of water and most organic molecules as well. The ionized form we could see is H+. H+ here, that is a proton, and it makes body fluids more acidic. So anytime we have, let's say, a container here, and it has some sort of liquid in there, let's say water, and you start dumping in protons, or in this case, hydrogen with a plus, the more hydrogen that gets dumped in, the more acidic it becomes. Okay, just think of in the stomach, we have something called hydrochloric acid, HCl. Hydrochloric acid. It's because of those hydrogens right there, the hydrogens. Okay. Nitrogen, N, is a component of all protein and nucleic acids. What are other elements that we made up of? And obviously smaller amounts, okay? So remember the major elements, CONE, that makes up 96%. And then we have these lesser elements like calcium and potassium and sodium and chloride. I mean, magnesium, such a small percentage, but yet it is extremely important for the human body, especially to make energy. We need salt, we need electrolytes. Sodium chloride is extremely important as well to help generate action potentials in the body, to make nerves work, to make muscles work. They won't function without sodium chloride and even calcium. When we talk about phosphorus, that P, we see that P in ATP. There's the P, adenosine triphosphate. We need that for ATP. We need it for energy. All right? Okay. So let's move on. Again, this just gives you just a pie graph to show you the significance of, right, the major elements making 96%, the lesser elements 3.6%, and then you have trace elements of 0.4%. Chemical elements are composed of units of matter of the same type that are called atoms, and atoms are the smallest unit of matter that retain the properties and characteristics of an element. In this particular illustration, you can see right in the center is the nucleus. And the nucleus is made up of neutrons and protons. And then you see these electron shells around it, which is where the electrons are contained. They move around in the electron shells. An ion, an atom that has lost or gained an electron. So why would we have something that's going to gain or lose electrons? It is for stability. It can, in this outer shell, let me go back here, in this outer shell we need to have at least 8 electrons for stability. If there's more than that, that's free radical. So it wants to get rid of one of those electrons, and maybe it'll donate it to something else. We'll see that in the classical example of ionization when we talk about sodium chloride goes through a process called ionization, where one of those elements is going to gain an electron, one's going to lose it, and they work in harmony together. A molecule is two or more atoms sharing electrons, and a compound is a substance that can be broken down into two or more different elements. I'm not going to show this link here in the video. I want you to make sure that you open up the PowerPoint separately. Make sure you have an internet connection, and then click on that link. It'll probably take you to a 3 or 4 minute video on chemical bonds. The animation is really important. I couldn't possibly draw out or show you in a flat dimension as good as this animation does. So please take the time. It'll help affirm that information for you. Chemical bonds occur when atoms are held together by forces of attraction. The number of electrons in the valence shell determines the likelihood that an atom will form a chemical bond with another atom. And we'll show you how that works in a few minutes. You should be familiar with cations and anions. Be familiar with them. So hydrogen is H+, sodium, Na+, potassium, K+, magnesium, Mg2+, calcium, Ca2+, iron, Fe2+. If we look at chloride, Cl-, this is an anion. Hydroxide, OH-. Be familiar with bicarbonate, HCO3-. Sulfate, SO4, 2-. And phosphate, PO4, 3-. Okay, be familiar. Cations, just look at the easy way to remember this. Let me show you. Easy way to remember cation. The word cation has a T, looks like a plus sign. Okay, the anions have two ends for negative. That's these here. Okay. Atoms are the smallest unit of matter that retain the properties of an element, and atoms consist 3 types of subatomic particles: protons, neutrons, and electrons. So the nucleus right here is composed of protons and neutrons. And then we have electrons, which surround the nucleus in the electron clouds or the electron shells. Protons are positive. If you take 2 protons and pull them together, they'll repel. All right, if you take 2 electrons and bring them together, they can repel. So when you bring 2 like charges, just think of 2 people that are too much alike, they'll repel each other. You also heard opposites attract, right? In relationships, 2 different people with different personalities, one's positive, one's negative, they get along well. So here in the nucleus is made up of a bunch of protons that come together. So if those protons are going to repel, it'll rip apart the nucleus. So we buffer it by throwing some neutrons in there so it doesn't rip the nucleus apart. Okay? So the electron shells, most likely region of the electron cloud. This is where we're going to find the electrons orbiting the nucleus. The first shell, which is here, let me just put on the pen again. So here, this is the first shell. We're going to circle it 1, and then here is the second shell. In the first shell, right here, it can only hold 2 electrons. So there we have 1, 2. In the second shell, it can hold up to 8 electrons. The third shell can hold up to 18. But the golden rule is what we call the Octet Rule, where we want to see at least 8 electrons in the outer shell for stability. So here's 1, this would be 2. If there was another one here, 4. If there was another one here, 6. And if there was another electron here, that would be 8. That would be very stable. Okay. Typically, the number of electrons will equal the number of protons. So let's take a look. The atomic number is the number of protons in the nucleus. The mass number is the number of protons and neutrons. So let's say we look at where's sodium. So sodium, there's 11 protons, 12 neutrons, so the mass number is 23. The atomic number is the number of protons. So you can see the number of protons is 11, that's the atomic number. And usually the number of protons will equal the number of electrons. There's usually the same amount. Okay, so this is kind of important, and I'll show you why in just a few minutes, where if we look at the atomic number of sodium being, let me turn on my pen again for you. Let's use blue again. So if we look here, the atomic number is 11. So I'm going to draw this out here. So let's say here's the nucleus. Let's say here's the first, here's the second. So let's put 11 electrons there. How many can fit in the first cloud? 2. So here's 1, here's 2. So we have 2 so far. How many can fit in the third layer? In the second layer, I'm sorry, 8. So here's 1, 2, 3, 4, 5, 6. Sorry about that, it's not the neatest. 7, 8. So how many electrons do we have all together so far? So we know we have 8 in the second shell, and in the first shell we have 2. 8 and 2 is 10, but how many do we need? We need 11. So what do we need to do? Well, we need to add another layer here, and we're going to throw 1 electron there. Now we have 11. Whoa, stable or unstable? Remember, the Octet Rule tells us that we need to have at least 8 electrons in the outer shell, and this only has 1. So this has the potential of doing a lot of damage. That's called a free radical. That's an oxidant. It's damaging. So we can have our good friend here, chlorine, which is next to it, which has an atomic number of 17. Well, let's see if we can make that come together. So here's the nucleus. Let's put our first electron cloud. We know that 2 can go there. So that's 2. How many can go in the second? We know that we can have 8. So I'm just going to make, instead of circles, I'm going to make lines. It's just easier with this. So here's 2 electrons, 4, 6, and 8. So now we have 8 plus these 2 is 10. How many do we need? 17. So what does that mean? Add another electron cloud layer. So let's do that. So now we have 10. How many more do we need? 7. So let's do it. Here's 2, 4, 6, and 7. Uh-oh. What rule was violated here? That's right, the Octet Rule says we have to have 8 in its outermost shell for stability. So what can happen? Let's take a look. Can something magical happen here between these two? Well, yes. Can we get rid of this one here, this electron? Can this electron move here? Yes, it can. When it does, now we have this, has 8. We then lose, I'm going to cross this one out, right? This entire electron cloud is not needed. And we have sodium, Na, which became more positive. Why did it become more positive? Well, it became more positive because it got rid of an electron. And then here is Cl, which is chlorine, and it gets the negative. Why did it get the negative? Because it took an electron from sodium and absorbed it at chlorine. When electrons are negative, it becomes more negative. So the negative and the positive give you some information. This one was a proton donor, and this one was the proton acceptor. Okay? And that's how bonds can be formed. Okay, that's called ionization, right? You've heard of ionized salt. Okay, moving on. Hope you guys are doing good. You can absorb that information. So this is what we covered already. We said that bonds hold together the atoms and molecules and compounds. An atom with a full outer electron shell is stable. We talked about the Octet Rule. It states that biologically important elements interact to produce stable arrangements, but you need 8 electrons in that outer valence shell. So we can do that by a few ways, meaning electrons can either be shared, which we didn't see before, right? What we saw was a losing and gaining type of relationship between sodium and chloride. That's called ionization. We saw that sodium lost an electron, and we saw that chloride gained an electron. Okay, sharing is something different. Those are called covalent bonds. So there could be covalent bonds, or there could be ionizing bonds. Free radicals are unstable. They're highly reactive. What you may hear about in healthcare is this term that is referred to as reactive oxygen species, also known as free radicals. These reactive oxygen species are oxidants. And what does the body use to combat that? We spoke about that earlier. We have superoxide dismutase, or copper zinc superoxide dismutase, which protects the cytoplasm. And then you have manganese superoxide dismutase, which protects the mitochondria. We have vitamin C, which has antioxidant properties. We have glutathione that we mentioned that has antioxidant properties. Especially now in times of COVID, we know that people with cardiovascular issues, diabetes, high blood sugar, metabolic issues just means that the mitochondria are having challenges making energy. Okay, these people have less amounts of glutathione. So utilizing some form of glutathione and vitamin C is very helpful. Also zinc. There's lots of evidence pointing to zinc to help the immune system. Why? Look at the cell. Copper, zinc, SOD. This is why zinc has a very, very good reputation in helping the immune system. Okay. Free radicals. These are produced in your body by absorption of energy in UV light and sunlight, in X-rays, by the breakdown of harmful substances. So what we mean is the breakdown of harmful substances. So we know alcohol overall is bad for the body. Drugs are bad for the body. Any foreign chemical that enters the body is very damaging. But the body has to detoxify it. And guess what does the detoxification? The liver. The liver has phase 1 and phase 2 of liver detox. If you go to Google Images and you type in liver detoxification phase 1 and phase 2, you will see a great image that shows the detoxification process. Toxins come into the liver, and they come in as fat soluble. And it has to work hard to make it more water soluble so the body can excrete those toxins through urination, bowel movements, and sweat. So phase 1 takes them and it tries to make them more water friendly. Okay? And then phase 2 helps a little bit more to do that. Now, between phase 1 and phase 2 of liver detoxification, there's free radicals that are produced. So even though detoxification is very important for the body, if you do a detoxification program without being properly supported by antioxidants, you can do a lot of harm to the body, lots of harm. So it's really important to do it with doctor's supervision for sure, just to make sure the body is prepared to handle that detoxification. The normal metabolic reactions, like the mitochondria, produces free radicals, fried foods, smoking, drugs, and even exercise. We know people that run marathons that die the next day. Why? Their bodies produced an incredible amount of oxidative stress through the mitochondria producing all that energy and giving off its exhaust, which is oxidants, and it surpassed the body's antioxidant capability. When the oxidants are in higher concentration than your antioxidant quenching capability, you do a lot of harm to the body. Okay, so you always want to make sure that your antioxidant capability is healthy to quench the oxidants. Free radicals are linked to diseases like cancer, diabetes, Alzheimer's, atherosclerosis, and arthritis. The damage may be slowed down with antioxidants such as vitamin C, vitamin E, selenium, vitamin A, or beta carotene, which is the precursor to vitamin A. And this is something that I find fascinating, is increased serum thiol levels. There have been studies done with chiropractic patients that have been a long-term study where they followed maintenance patients for about 2 years. And what they discovered was that their serum thiol levels were much higher than the average person. Well, why is this important? This is very important because thiol levels protect telomeres. The telomeres is the protective cap to your chromosomes. And what they discovered is that the longer the telomere, the longer your cells live. The longer your cells live, the longer your tissues, organs, systems, and organism lives. The shorter the telomeres, the shorter the lifespan. The longer the telomeres, the longer the lifespan. So what was discovered, and this is fascinating, I've been in practice over 25 years, and without question, the majority of the patients that I've treated come in and say they've been healthier this year, or it's the first year they didn't have allergies, or they don't have migraines anymore, or their aches and pains that they've had for so many years are no longer with them. They're not suffering with them. And my mentors and old timers from years ago, they had a saying, and their saying was that chiropractic added years to life and life to years. And they didn't really understand the science behind that. I mean, they knew as much as saying that if your neurology and your neural system was clear of any interference, then all body systems function better. And that is true. But now from a biochemical standpoint, not from a neurological standpoint, but from a biochemical standpoint, they're looking at the genetics and they're looking at the chromosomes. And people who are under care for 2 years or more, they have higher serum thiol levels. So what they're now discovering is that when patients receive an adjustment, not only for their neck pain or back pain, but for overall wellness, their bodies have the capability of producing higher serum thiol. And this is like groundbreaking information. So it takes the adjustment into a whole different realm when it comes to healthcare, not just helping people with their aches and their pains and neck pain and back pain, but in terms of longevity, in terms of lifespan. So that's really fascinating information that's out there. Ionic bonds, let's look at cations versus anions. This picture, this illustration shows what I was trying to demonstrate before, where if you look at the top, this is sodium. If you look at the bottom, this is chloride. And here an electron was donated to chloride to make this stable. So sodium has the plus sign, chloride has the negative sign, and we have this nice relationship formed by this ionic bond called sodium chloride or salt. Now, that is a losing and gaining relationship. Here we have covalent bonds. Covalent bonds is sharing, right? Sharing is caring, okay? So here, hydrogen only has one electron. So hydrogens by themselves are unstable. But if we bring two hydrogens together, then we get H2. And it gives the illusion or the feeling that in that first shell, there's two electrons. That's stable. When we look at oxygen, oxygen has 2, 4, 5, 6. 6 electrons in its outer shell, unstable. But if we bring two of these oxygens together, so we get O2, and we count the amount of electrons in the outer shell, well, we have 1, 2, 3, 4, right? In the link, in that center link, 4, 5, 6, 7, 8. If you count in the other one, again, 1, 2, 3, 4, 5, 6, 7, 8, stable. The same thing holds true for nitrogen, okay? N by itself, not healthy, but you bring two nitrogens together to form N2, we have a stable molecular formula. And there's just a few other examples of that. You can see carbon. Here we have other covalent bonds where if you look at carbon, there's only 4 electrons in the outer shell, and we know that each hydrogen has 1 electron. So here it's pairing 1 hydrogen to each electron in the outer shell, creating CH4. Here is another one where we have oxygen by itself, and we can bring 2 hydrogens. Each hydrogen has 1 electron, creating H2O. Pretty neat how the innate intelligence of the body can do that. Hydrogen bonds results from the attraction of oppositely charged molecules. Again, you can have hydrogen, which is a positive charge, oxygen has a negative, and they bind, H2O. Hydrogen bonds between water molecules give water cohesion. Cohesion is the tendency of like particles to stay together. Hydrogen bonds create surface tension. It allows spiders to walk on the top of the pool. It allows a bug to hit your eye and then it pushes it out, right? It creates surface tension. Surface tension is a measure of the difficulty of the stretching or breaking the surface of liquid. Let's look at some chemical reactions, if we would, okay? Chemical reactions occur when new bonds are formed or old bonds are broken. We have reactants, which is the stuff you start with, and then we have products, the stuff that you end up with, okay? And metabolism is the process through which things are produced. Things that can be produced from breaking things down or from building them up, catabolism or anabolism. Energy is the capacity to do work, right? We know that. Oh, Doc, I couldn't get my work done. I didn't have enough energy. I worked all week, right? So energy is the capacity to do work. In terms of energy, there's potential energy, kinetic energy, and chemical energy, and we'll talk about each of these. The law of conservation of energy, energy can either be created or destroyed, but it can be converted. It can be converted from one form into another form. So energy is the power to do the work. Work is a change in mass or distance. So if I walk from point A to point B, I did work, and that took energy. If I changed water into steam, that change required energy to do that. Kinetic energy is energy in motion, whereas potential energy is stored energy, right? You have the potential. A battery has potential, but it doesn't do anything until it's plugged into something. Kinetic energy, if you put a ball on the top of a mountain, it's got potential. Now, once you give it a little push and it rolls down the hill, that energy in motion is called kinetic energy. Chemical energy is potential energy that's stored in chemical bonds. When chemical bonds are broken, it releases energy. when bonds are broken, when bonds are created, it takes energy to make them. When a bond is broken, it releases energy into the system. Cells perform work as they synthesize complex molecules into and out of a cell. If we think of skeletal muscle like the biceps or the triceps, when you're sitting still or you're at rest, they have potential energy. They have potential energy in the form of protein filaments and the covalent bonds that are between the molecules inside the cell. Now, when the muscle contracts and is performing work, now think of what happens when you exercise. Your muscles are performing work. It takes energy in order to do that. And we now have potential energy that's converted into kinetic energy. When that happens, it releases heat. We know that when you exercise, you feel warm inside, you get hot. And to cool your body off, we sweat and perspire to release some of that heat. Types of chemical reactions: synthesis, to make; decomposition, to decompose, to break down. We'll show you an exchange reaction, a reversible reaction, and what does oxidation and reduction mean. So synthesis reaction is when you take two or more atoms, ions, or molecules, and you combine them, you bring them together to form a new and larger molecule. All synthesis reactions in the body together, we call it anabolism. Anabolic, not catabolic. Anabolic is building up, catabolic is breaking down. These are endergonic because they absorb more energy than they release. Dehydration synthesis, you're going to hear that term, right? This is a synthesis reaction. Dehydration synthesis or condensation is the formation of a complex molecule by removing water. And it's the opposite of hydrolysis. So we're going to show you chemical reactions that could be a two-way street. When it goes in one direction, it goes through dehydration synthesis, and when it goes in the opposite direction, it's hydrolysis. In fact, let's see if I can show you that, and then I'll come back. Let me just see if I can find, here it is. So let's just take a look at this illustration here down below. In the middle right here, you see dehydration synthesis and hydrolysis. So on the left, all the way on the left, we have glucose. We see it's a hexose sugar, C6H12O6. At each corner, there's a carbon. And then here is a pentose sugar. It's at 5 sides, fructose. When we bring these two together, glucose and fructose, and we move in this direction, we can get sugar, sucrose. But let's see what happened. It needed to go through dehydration synthesis. We're taking two smaller reactants to get this product. We're taking glucose, which is a monosaccharide, and fructose, another monosaccharide. We take two monosaccharides, bring them together to get a disaccharide, sucrose. In order to do that, look what it did. It took this hydrogen from fructose, right there in the center, and it took OH, hydroxide. It brought these two together. You see there's two hydrogens and an oxygen. And on the other side of the equation, there's the two hydrogens and oxygen, water. So it created a disaccharide plus water. Now, hydrolysis is moving the opposite way. It's taking sucrose. Let's say you added table sugar to your food to make it sweeter. How is your body going to break that down? Well, it takes the sucrose with the water in your body, or the water that you're drinking, which is H2O. It's going to take the two hydrogens and the oxygen, put them back in. It's going to break down. Hydrolysis. Lysis means to break down. Hydro is water. So it's going to take that H2O and put back the two hydrogens and the oxygen to get our two original monosaccharides. Okay? Dehydration synthesis. Synthesis, you're taking something smaller, making it larger. Hydrolysis, we're using water to break something larger down into something smaller. That's why you drink a little water with your food. It makes it easier to break down. Okay, let's go back. Let's go back here. So that visual should help you with the synthesis reaction and with this one here, decomposition, which is catabolism. This is where you have the larger molecules are split into smaller. That's where we took sucrose and broke it down into glucose and fructose. That's catabolism. These are exergonic because it releases more energy than they absorb. Catabolism is when you take AB and it's broken down into A plus B. This is sucrose, AB, and it's broken down into glucose and fructose. We use catabolism when we're breaking down proteins, fats, and carbohydrates that are too complex in what we're eating, and it uses strong digestive enzymes to break them down. Okay? That's why good digestive enzymes in the stomach are important to break down your proteins. Again, decomposition involves hydrolysis. In this case, we're taking water and we're breaking it down, and you saw in that reaction where it took fructose and sucrose, it took hydrogen from one and it took the hydroxide from the other, and it brought it to the opposite side. All right. When a covalent bond is broken, it releases kinetic energy, and that energy can perform the work. Every single thing, right? Every process that takes place in the cell that's performing its vital functions needs energy. An exchange reaction here, we see that on one side we have hydrochloric acid plus sodium bicarbonate. And all it's doing is exchanging. It's going to reorganize these things to give us bicarbonate and sodium chloride. So if you look, here's one hydrogen, here's the other. All it did was bring those here to give us H2. Then we see here sodium on the left, we see sodium on the right. We see chloride on the left, chloride on the right. So an exchange reaction, it's just reorganizing everything. Reversible reactions, as it sounds. AB can become A plus B, or A plus B can go back and form AB. The body has a lot of reversible reactions, especially when we talk about pH and pH balance. We have this reversible reaction between carbonic acid and bicarbonate in order to monitor pH of the body. And here we see a classical example of taking carbonic acid, which is H2CO3. We're adding hydroxide to it, and then we're left with something called bicarbonate, which is an alkaline or a base. We can take bicarbonate, which is more alkalinic or basic, add a hydrogen to that, and then remember, whenever you add hydrogen to something, you're making it more acidic. So now we have carbonic acid. We know that this buffering system is reversible. It goes back and forth to help monitor pH of the body. So you can have carbon dioxide plus water, gives us H2CO3, which is carbonic acid. If we become carbonic acid, the body can then break that down into bicarbonate. It can go in either direction. So the reaction transfer of electrons between atoms and molecules and always occur in parallel. When one substance is oxidized, one is reduced, right? If one is gaining an electron, the other is losing an electron. So the term oxidation refers to the loss of an electron, and the term reduction involves gaining an electron. Okay? So there's a little mnemonic that's called oil rig, an oil rig. OIL, oxidation is losing, and then rig, RIG, reduction is gaining, oil rig. That's how you can remember that. Okay, let's look at inorganic compounds. Inorganic compounds usually lack carbon and are simple molecules. Water is an important, and water is the most important and abundant inorganic compound in all living things. Organic compounds always contain hydrogen. They usually contain oxygen and always have covalent bonds. Again, I'm not going to click on this link, but I want you to download just the PowerPoint. Click on this so you could watch the animation of the properties of water. It'll give you a stronger understanding. We're going to be concerned primarily with water and how its properties are essential for life. Most other inorganic molecules exist in association with water. Both carbon dioxide and oxygen, for example, are gas molecules that are transported in body fluids. All inorganic acids, bases, and salts dissolve in body fluid as well. Water is what we call the universal solvent. Water makes up about 2/3 of the total body weight. The bonds in water are oriented in such a way that the hydrogen atoms are close together. And as a result, the water molecule has a positive and a negative pole. So water is called a polar molecule. Remember, oxygen is the minus, the hydrogens are the positive. Negatives and positives attract to one another. Many inorganic and organic molecules will dissolve in water. When it does, remember, water is the universal solvent. When you're dissolving something in there, you get a solution. What you're dissolving in the solvent, what's being dispersed in there, is the solute. Okay? So solvent is the universal one, is the water. Let's say you put in sodium chloride in there. Sodium and chloride would be the solutes. And then what you're left with is this solution. Water has high heat capacity, right? We know we can use it to put out fires. It's got a cohesive nature of water, meaning it allows things to move smoothly through, let's say, blood vessels and tissues and spaces. It's very important to allow things to move smoothly. It's like a lubricant. And down below, you see that water is also found in the respiratory tract and the digestive tract. It acts as lubrication through there. It's found between your joints, in between all of your movable joints, like your elbows, your shoulders, your fingers. Every joint that's freely movable is called a diarthrotic joint. It's freely movable, but there's lots of synovial fluid there. Extremely important. You find it between the chest and the abdominal cavities. They have serous fluid in there, not mucus, but serous fluid. It's something different found between organs that allow them to slide past each other. Okay, we said water is a polar molecule. We discussed that before. Here, water is the solvent. So we can see on the left is sodium chloride, and when we disperse it in water, it can dissolve, it can separate the sodium from the chloride. Water is the ideal medium. We spoke before about hydrolysis reaction compared to dehydration synthesis. In hydrolysis reaction, water is added to break the bond. That's going from right to left. In dehydration synthesis, water is removed to make the bond. That's going from left to right. Here on the top, we have hydrochloric acid on the left. We're dispersing that into water, and it dissolves into a proton, which is hydrogen, and an anion, which is chloride. That's an acid. Whenever you dump hydrogens, when the water becomes more filled with hydrogen, that solvent becomes more acidic. Now we have potassium hydroxide. It dissolves in water. You get potassium. That's the proton. And then here's the anion, hydroxide once again. So here you have hydroxide. When you have more hydroxide in a solvent, then it's an alkaline or a base. All the way on the right, potassium chloride. When they dissolve into a proton and an anion, I should say a cation and an anion, right? I think I used They are protons, but protons really deal with hydrogen. But here with potassium and chloride and potassium hydroxide, if we look at the middle one again with potassium hydroxide, the potassium is the cation, the anion is hydroxide. On the right with potassium chloride, potassium, the K, potassium is the cation, chloride is the anion. When something dissolves into an anion and a cation, of which neither of them are hydrogen or hydroxide, it's not an acid, it's not a base, we consider that to be a salt. An acid is a solute that adds hydrogen into a solution, that's the proton donor. A base is a solute that removes hydrogen ions from its solution, so that's a proton acceptor. And weak acids and weak bases, these fail to dissociate completely, and they help to balance pH. Here we're looking at a pH scale right in the center. Right in the center, we have neutral, which is a 7 pH. Anything less than 7 is considered to be acidic. And then anything greater than 7 is alkalinic or extremely basic. We can look at things like stomach acid on the left, very acidic. If we look at things like, let's say, blood pH is around 7.35 to 7.45, so an average pH of 7.4, that's slightly alkalinic. If we look at ammonia, very alkalinic or basic. When we look at foods like tomatoes, grapes, vinegar, wine, and pickles, these are very acidic. So this also looks at things like gastric juice in the stomach, has about an average pH of like 2.3. Lemon juice also 2.3. Vinegar, very acidic. And then we start moving up. The higher the pH, now we're moving more basic and alkalinic. Okay. We look at blood, there's blood 7.35 to 7.45. It's a very tight range. Okay, we know how important pH is. pH is important to pools, right? The pool water pH has to be perfect. Fish can only live in a certain pH of water. Women understand the importance of vaginal pH, that if that goes off, you can get bacterias or vaginosis. So extremely, extremely important. Again, I want you to click on acids and bases and watch that short video tutorial on acids and bases. We talked about buffering systems to help regulate pH, where we're going from bicarbonate to carbonic acid, and the arrows are going in both ways. Okay? All right, I'm going to pause here. Now that we've done the introduction to chemistry, we're going to pause, and we did inorganic compounds. We're going to start organic, but I'm going to stop this video, and we'll do organic on a separate video. Okay?